Thank you. I think we've got all the working group chairs at the table there now. Thanks. For those of you who were at the opening of the conference, you may have heard the minister referred to NISI, or the Northern Infrastructure Standardization Initiative, and that's something that isn't well known yet amongst a lot of players in the design community, although a number are actually actively involved in the working groups. But today, hopefully you'll understand a little bit more about the initiative and how it ties into climate change, and in particular related to permafrost. The adapting infrastructure to climate change, including changes in temperature and precipitation patterns, will have a significant impact on our northern communities, and you may be seeing some of that already. The impacts can be wide-sweeping. Basic cost implications, sustainability, and even insurability of infrastructure can be affected. Foundation design in permafrost is just one example of where these impacts are already evident and creating challenges for our engineering community. We've seen a number of incidents, as you saw in some of the earlier slides from other presenters, where our foundations are a particular challenge. And the thing about foundations, of course, is that if you get them wrong, they're very difficult to repair or fix. They're also often a lifelong problem and high cost to maintain. Adaptable mechanisms that decrease the North's vulnerability to climate change impacts are therefore needed and in the public interest, as well as the interest of designers, builders, and developers across the northern territories. One tool that's available to assist Northerners in addressing climate change risks to infrastructure is the application of standards. And it's something that there hasn't been a lot of in the past, which are development of northern standards for Northerners and use in this environment. A lot of the standards have been developed nationally, but in this case, this effort is specifically focused on standards developed for the North by Northerners with the best experts we can find across the country to support that process. The Northern Infrastructure Standardization Initiative, or NISI as it's often called, is a 5-year project. It started in 2011, goes through to 2015, and it's funded under the Government of Canada's Clean Air Agenda. And it's one of the few projects that came forward back in 2011 that was approved under that initiative as a new project. The Standards Council of Canada, which you'll see represented here, leads the Northern Infrastructure Standardization Initiative in partnership with Aboriginal Affairs and Northern Development Canada, under the advisement of the Northern Advisory Committee, which is something that a lot of people may not be aware of. The Northern Advisory Committee is a committee that I have been chairing for the last year. It actually is comprised of senior representatives from all the governments across the territories, usually the Assistant Deputy Minister level positions in those departments. We have the Yukon, Northwest Territories, Nunavut, and Katvik, Nunavik represent the Northern Quebec area. The main deliverables for the Northern Infrastructure Standardization Initiative include development of new standards intended to strengthen infrastructure in the face of climate change, as well as building capacity to ensure that these standards are implemented. And that can be a challenge because different regimes or different jurisdictions have different ways of implementing or enforcing standards or building codes across their particular areas. The Northern Advisory Committee provides direction and established priorities for the Standards Council of Canada to move forward to engage the technical services necessary to support the development of the standards. NAC will help ensure that the deliverables are relevant in a northern context and in the best interests of Northerners. And I'm very pleased with the amount of Northern involvement and the extent of the stakeholders, Northern stakeholders involved in these standards. The NAC committee has prioritized current focus areas for 4 standard developments for NISI. The first one, as you'll see here, is community drainage system planning, design, and maintenance in northern communities. And for those of you who work with northern communities, you know how critical this becomes. Drainage, whether it was today or 20 or 30 or 40 years ago, has been an issue in many of our communities. And from my perspective, being up here for 34 years, I think it's a very positive sign that we're actually going to start looking at standards in that area. Drainage, of course, affects not only your own development, but your neighbors and everyone else. Managing changing snow load risks for buildings in Canada's north, something that many of us are already experiencing and seeing impacts in our particular areas. Not only is it the climate change snow loads that we see in terms of the volume of snow, but you also see the type of snow changing, and we're seeing much wetter snow in some areas and much different snow patterns in other areas. Thermal siphon supported foundations, we heard about that just a few minutes ago. Developing standards for that for use in permafrost is another key area for us to look at, and the importance of that particular foundation system into the future will probably be self-evident as time moves on. Moderating the effects of permafrost degradation on existing structures is another area of concern. there is, or there will likely be impact on structures as they exist today, and we're already seeing some. How to moderate those impacts, how to address those in a cost-effective manner is something that we all have to concern ourselves with. Looking ahead, the NAC has also raised the need for the development of a mechanism to sustain northern governance regime to prioritize standards for the north. So it's one thing to implement standards, but you also have to maintain a governance regime looking forward. And I can tell you from my experience on the committee, we're also already looking to the next round of potential standards that might be of interest in the north for northern designers and builders. The Canadian Standards Association Group has been contracted by the Standards Council of Canada to facilitate the standards development process. So there, through a procurement process, we engage the Standards Council of Canada to actually develop the standards. And the CSA group has put together 4 working groups and 1 overarching technical committee to oversee the whole process. These groups are comprised of representatives from technical experts from northern governments, industry, operators, construction, and other sectors of the north. And in some cases, it's actually municipal governments and municipal representation on these committees, especially for things like drainage. The chairs of the 4 working groups are here today to provide you with an introduction to the standards, including discussion of the scope and the document and the content. It's interesting that not all these standards are the same and they don't have the same challenges. Each one is unique and involves a different number of stakeholders and different interested parties. For example, the thermal safety standard is already out for public consultation, and we encourage everybody to get a good look at that and provide feedback into that before we move it to the next stage. And with that, and in the interest of time, I think I'll start introducing the various chairs of the working groups. So first of all, we have Mr. Ken Johnson. Ken is with Standec Consulting Limited and is the chair of the working group for the community drainage system planning, design, and maintenance in northern communities, and he's going to give you an overview of that particular standard development. Ken?
And I will apologize in advance. We've got 10 minutes to give an overview. Thank you, Mike, for that introduction. And I think he was talking about the different stakeholders, and in fact, something that's unique to our committees. We've got planners, engineers who generally don't get along at the best of times, as well as the maintainers. I happen to be a planner and engineer, so if you see that sort of that quirk, it's the left, right in conflict. Anybody who's been up north for any period of time, you can go into communities and you can see the community drainage. Roads and drainage are a major chronic problem that have been, as long as communities have been in existence in the north. This is a shot that I got a hold of when doing some climate change work in Kugluktuk. And it's sort of one of the more dramatic shots I've seen of a storm event back in 2007 that did some major damage. So the group in our group includes Yukoners, NWTers, and Nunavut's. So we've got a broad background, planners, engineers, and operations staff that is coming together. And none of us had come to this table being at all involved in the CSA standard. So that, in fact, has been sort of one of the introductory roles. We can talk about engineering, planning, and design and maintenance in the context of our individual disciplines. But actually putting that into a context of a standard has been a great challenge. We've learned a lot, and we still have a long ways to go, as our CSA master says, but we're getting there. So I'm going to just be doing an overview and give some of the background and then sort of where we're at and what we've learned. These are just some examples, and again, this is from the newspaper Iqaluit in the spring of 2013 with cars, and its spring melt and rains exposed the weaknesses in Iqaluit's roads and drainage. The spring of 2013 in Rankin, they had 92 centimeters of snow, which was essentially a year's worth of snow in a couple of days. These are sort of some examples and say, okay, drainage, as important as it has been for decades, and in fact, it's turning out to be an increasingly important factor as we're involved more with climate change. Kimmeroot flash floods. This was back in spring of 2012, and where they had a snowslide and public safety issues associated with that. And then in March of this year, they're still worried about huge piles of snow in the community. So we're talking about a broad range in terms of the actual infrastructure, but all the snow as well as rain and all the climate events that are associated with moisture. But what do we have in terms of drainage systems today? I had was fortunately involved with a climate change project in Kugluktuk and had the opportunity to wander around town for days, just looking, as they say, the engineering side of me, looking at the drainage system in detail. And Lewkowicz has rudimentary drainage in terms of ditches and culverts, but those systems are in various stages of disrepair. So I think that's important to this overall element of drainage, is that you have the planning and design, but the maintenance is in fact is sort of will actually dictate the success of this program. That's why we're in developing this standard. We expect the standard language to be this thick and our appendix to be that thick, recognizing that the pullouts and the additional supplementary information that we can provide to community maintainers will dictate the ultimate success of this standard as we're envisioning it now. But this goes to show in terms of who's responsible. Kikatarjuik flooding and erosion back in June of 2012, they had some issues with the flooding, and they were talking about damage in the $250,000. So regardless of how the planners and engineers are involved in it, it comes down to the community is responsible and has the long-term responsibility for maintaining and improving that drainage. And I think that is sort of the key to that, the whole success of our exercise. So the operation maintenance, so as I already said, and these are shots from around Lewkowicz in terms of talking about things such as plug culverts, drainage channels or ditches that are improperly maintained, culvert ends, and I mean, this is standard stuff. And really these are the elements that we're looking at in terms of trying to bring forward the planning side, which community planning is a fairly well established exercise in most northern communities. Most northern communities have a community plan that has drainage elements in it. And these plans are updated quite sporadically, but the drainage is sort of inherent too. It's now trying to take that information, that element, and bring it forward to a sort of a new level where you've got information available and you've got it in the context of a standard. As I was just saying, there's an integration of existing information. This is the community plan for Repulse Bay in Nunavut. And drainage is, I say, a standard part of the language within the community plan. But as we've been talking about, and this was sort of one of the fundamental interests that I had for coming to here, is talking about the terrain hazard mapping and the satellite imagery that is now available and now in fact becomes a tool. And this was part of our learning curve as part of this process, is saying, okay, what do we need in terms of drainage planning and design? And the classic is, well, let's do a topographic map of the community. Let's send surveyors in and collect the sub-centimeter topographic information that we can actually do in the design. But now we're bringing into the other elements. What about the permafrost areas or the areas that are prone to erosion? How do we bring those elements in without a fairly significant geotechnical exercise? Well, we've got the imaging now that I think can bring those elements into play. So this is really sort of the tail end, and I think I'm pretty much on topic. Coming together with our group, we had the opportunity to meet here in Yellowknife back in August, and we have such a broad range of planners, engineers, and the maintainers. We came into the room, we had a draft, and I think by the end of it, we'd pretty much thrown out the draft, and we're not starting from scratch, but we certainly learned in terms of what we're trying to do with our standard documentation and what information we really want to include. So as it stands now with our committee, we're focusing on imagery to convey the planning, design, and maintenance. Very important, and I think this is sort of where the planning elements is, that from a planner's perspective, we have to be very, very visual. We want to convey that in terms of understanding and conveying the message. We want to make sure the standards language for the planning, design, and maintenance is appropriate to the actual standards within the CSA context. And again, a very important, and we're working on that. But I think where we're really concentrating, or a lot more energy will go in terms of the appendices and a lot of pull-out stuff, maintenance and other relevant checklists. And this is where I say, going to plug, if anybody has any ideas that have just come to mind right now, we would certainly appreciate that input. As we're finding out with our various committee members, we had a drainage standard that one of our committee members brought out, I think, for Fort St. John or Fort Nelson, and we had a look at it in the last 10 days and going, we want to include this in terms of an actual usable document to include in the standard. And I certainly would like to acknowledge our committee members. Dennis Althouse with the GNWT, Jack Bowers, Yukon Government, Bob Chappell, GN, Ed Cormier, GNWT, John Clark, Williams Engineering, Greg Cousineau, GNWT, Scott Lamoureux, Queens, Ian Robinson, a planning consultant in Whitehorse, and John Watson with the GN. Some of those gentlemen are here today. I won't embarrass them by standing up. And thank you very much for your attention.
Okay, thanks, Ken. I think we'll keep our questions to the end of the 4 presentations, if you don't mind, just in the interest of giving everybody a chance to get through their presentation. Ken, I really enjoyed that, in particular, the slides of Kuluktuk. My first job with the government of the Northwest Territories 34 years ago was designing some of those dams beside the road in Kuluktuk, those stone piles there to slow down the water flow so our roads didn't wash away. That was before the issue of climate change came up, but it's been a significant issue in that community for many years. My next guest, I have the pleasure of introducing Heather Auld. She's a principal climate scientist with the Risk Sciences International and has 34 years experience as a meteorologist, climatologist, and climate change adaptation expert. She spent 32 of those years with Environment Canada. Heather has extensively researched and developed engineering, climate, and climate change design values for the National Building Code of Canada and is a climate change adaptation focal point for the code. She is the chair of the working group for the standard Managing Changing Snow Load Risks for Buildings in Canada's North. So Heather.
Well, thank you. You must be getting a little bit tired now, so we'll try to keep this going. We've learned so far today about some of the power of snow, about its ability to insulate the ground so that the permafrost doesn't refreeze back. We've learned about its power when it melts and what it does for community drainage and damage to infrastructure. But on this particular standard, we're dealing with the weight of snow and the kind of damage it does. This is a picture of what happens when the roof collapses due to too much weight of the snow. So, okay, which one is... okay, got it figured out. Our committee is made up of largely engineers and building inspectors. We have a climatologist, and we have myself, another climatologist, and we have a municipal insurance expert. We may be adding to the committee, but my job, I guess, is to make sure that everybody in the group can communicate and keep on track. It's been said meteorologists have a lot of words for snow. Snow isn't just white. We have a lot of different measurements for snow. We have everything from snowfall to the depth of the snow on the ground to the weight of the snow on the ground. And then we have different estimates of snow density. We have snow loads, which is just the maximum weight of the snow that you'd expect on the roof of the building. And the building has to be able to withstand the greatest weight of snow you might expect about once every 50 years on average. We have a lot of other measurements that we use in meteorology, so we're really hung up on snow. In this case, this standard has to dance very nicely with the National Building Code of Canada. The National Building Code of Canada is usually adopted by the territories and the provinces, and it is gives the specifications for the design of new buildings, brand new buildings. This standard is dealing with another type of issue. It will have 2 annexes in it that deal with what to do with the fact that the snow is changing, and is changing quickly. What to do when you're designing new buildings, because that building has to last for 30, 50, 70 years, so you don't want to have it fail on you early. So this standard is going to focus, though, more on existing buildings. What do you do with those buildings that were designed at a time when the weight of the snow was less, and now it's increasing? How do you protect lives? How do you make that building last a little bit longer? And when should you get up on that roof and take the snow off? So there's 2 terms, two of those snow terms we're going to use today. One is ground snow load. What engineers typically do is they look at the weight of the snow that's on the ground, because that's sort of a constant. And then they use different factors to adjust it for what that snow should do on a roof, because every building's different. Every part of the roof can be different, and the wind can blow the snow around a different way. So the reference point is the ground snow load. What's the maximum weight of the snow on the ground? And then the roof, as I say, is very, very specific to the building. Typically, in the past, Environment Canada has calculated those ground snow loads, and then the building code says what to do with them. And they vary a lot from one community to another, or if you're dealing with mountainous terrain, you go a few feet up, and all of a sudden the snow loads are much greater as you go up in the elevations. Depends too on mountain ranges, so it's very, very locally variable. But it's worked well. We've been doing ground snow loads. The first values I could actually found were actually calculated around 1953. So we've been doing it. It's a challenge, but it's becoming a bigger challenge because the target is moving and the snow is changing in all different ways. The depth is changing, the weight, the wetness, and the weight of the snow is changing, and the amount of rain that we have falling on that snow is also changing. So you've got a lot of moving targets there to try to capture in a standard. Typically in the north, snow has been dry and wind-packed. Not happening anymore in a lot of locations. The snow and the maximum weight of the snow are behaving a little bit like it does in, say, parts of the prairies or parts of southern Canada. It's coming more in episodes now. Snow comes and it goes, and it changes more during the season, perhaps, than it did before, or not as consistently. So we know that the snow depths are changing in some locations, but not all. They're increasing. Pretty much snow is increasing most places when it comes to extremes. The accumulations, the amount that gathers over the season, the greatest depth you might see is also increasing in some regions. The densities are going up, particularly in the southern parts. The depths are often going up more in the northern parts of the Arctic. As I mentioned, the rain on snow is increasing, but the length of the snow season is decreasing. And we typically hear the snow cover is decreasing. That means the length of the year we have snow on the ground is decreasing. So people hear that and they go, oh, good, no problem with snow. No, the means and the different characteristics can vary in different directions. But the things that matter for buildings are increasing. And as I say, mean snow. You can have an extreme snow depth in a year when the snow that falls on the ground that's added up day by day is a minimum. So it can behave in really interesting ways. This is just a graph to show you what I have is the weight of the snow on the vertical axis, the snow load, maximum weight, and the year. And you can see it's all over the place, year to year. There's low snow years and heavy snow years, light and fluffy snow years, and wet snow years. And in the case, you can see that there was an event at Inuvik in 2004, and the dotted line shows what we would have likely designed that building for, the snow load. And you can see it went up above that year, and it bumped into the design value a couple of years later. So there's very specific types of data we love to have to do these types of calculations. Environment Canada has just updated the snow loads that are going into the building code that will come out in 2015. And just looking at the updated snow depth data, there's big changes coming for the north. Some communities aren't changing, but any of those that are going to see a changed weight of the snow that buildings have to be designed to will be looking for increases. You can see that in the chart at the bottom. In the Yukon, we currently have 9 communities listed in the building code. 40% of those are going up in the next code. In the NWT, 17 locations, 25% of those are going up, but the biggest changes, the biggest increases are in the NWT. And that's just based on the depth of the snow alone, not the density. And in Nunavut, 75% of the locations are going up. More moderate changes, not as big as in the NWT. So once the next set of studies comes in and looks at density, there's probably going to be more increases coming for subsequent codes. So this is something we're going to have to live with. And it's particularly an issue for existing buildings. So the crux of the standard is this when we get it finished, which is quite a challenge. We have to have procedures to reduce our vulnerability. If we have an existing building that was designed to withstand lower weights of snow, there are things we have to do to make sure that people don't get killed when the roof collapses, or the building doesn't have to be replaced prematurely, because that costs a lot of money. So the first thing, we have sections that will deal with how to reduce the risk, how to maintain that roof, how to make decisions on that building that are going to make sure that it can withstand those increasing loads where we can. Then we need procedures to monitor. We need to know, not every year is going to be a heavy snow year, but when it is there, we need to know when we're in trouble. When is that roof at risk of potential collapse? So that involves the sections on monitoring, and monitoring roofs, watching the roofs, and detecting when you're in a critical point where you're at risk of collapse. And then there's another section on how to remove the snow from the roof, because if you take the snow off the roof, your risk goes way down. Mind you, the risk to the person taking the snow off the roof goes way up, because a lot of people do slip and fall off roofs. There's quite as many, I think, probably see as many fatalities from removing snow as there can be from the roof. So it's a real tight balance there. So there's very strict guidance for safety reasons on how to remove that snow without killing someone who's doing that job or damaging the roof further. And when to seek engineering assessments. When are you so close to that margin that maybe you better get it looked at before the building is occupied much longer? And what are the warning signs? What kinds of things do you have to watch for a potential roof collapse? So when do you have to get out? So these will be the main considerations in the standard, because we have types of problems that are fast. When a snow load increases and a building's at risk of collapse, can happen quickly, and then there's the long-term things that we can do. So some of the things that will be there, okay. We'll be looking at, we will have to link, I think, with other projects to assess each building, because each building will be vulnerable in different ways. As I say, you can see here the graphics on how to safely remove the snow from the roof. You can see some of the warning signs. There'll be some graphics in there on what to look for when it's getting to be pretty darn unsafe. And one of our big challenges, though, is going to be snow data. It's variable quality, short records, sometimes not at all available in locations, not the right kind of snow measurement. So this is one of the biggest challenges in being able to detect when we may have a problem in a community for different buildings. So that will be a challenge. Snow densities are variable, and that's a problem. They're usually not monitored. Just with specific data, can we get that? We don't know what to do with rain on snow as yet. That's going to be other building codes to deal with that one. And we are still struggling with the question of when is snow too much snow? And when should you be up on that roof and clearing it? So there's a lot of challenges that lie with this standard. So I'm going to close it at that point.
Thank you, Heather. It's interesting, snow loads are not just a problem for building owners and designers. When you have a collapse or a failure in a building, and we've had a number over the last few years in particular where there's been problems, it's a community issue. And if anyone wants to verify that, if you talk to the community of Inuvik about what it was like to lose access to their arena for a whole year, no hockey, no other activities, figure skating, because it was full of students trying to go to school for a year because we lost a foyer in one of our older buildings. It's a community problem when these things happen. They're major. Another one we had last winter in Fort Simpson, where we had severe stresses on some of the roof trusses, and the school had to be, the kids had to be taken out of school for a few days until we could assess and beef up some of the trusses there. So there were lost days at school, parents who had to deal with daycare, all these types of things. It's a major impact when you have a roof collapse on a public building. And moving on to our next speaker, Antoni Lewkowicz is professor in the Department of Geography at the University of Ottawa. He's been a permafrost researcher for more than 35 years. His major interests have been in the distribution and characteristics of permafrost and the impact of climate and other environmental changes. He is the chair of the working group for the standard Monitoring the Effects of Permafrost Degradation on Existing Structures. Tony?
Thanks very much, and I would like to immediately acknowledge the efforts of the other members of the committee or the working group that you can see at the bottom: Ed Cormier, Steve Cockell, Jim Oswell, John Watson, Ed Hove, Richard Trimble, and Steve Wolfe. And as was said earlier, those of us who are involved with CSA for the first time have learned that there are all sorts of rules about the way CSA works, and one of the ways that they work is to make sure that the committees or working groups that are involved in developing a standard represent the different stakeholders. And so in this case, we have a mixture of researchers, engineers, and users on the working group, and it's important that we maintain that. So all of us are contributing to the development of this potential standard. So our objective, and here we see a building in Fairbanks, in fact, that is suffering problems because the original construction was done on the assumption that birch here would mean that there was no permafrost. Unfortunately, that didn't prove to be the case. And so our objective is to develop a Canadian standard for moderating the effects of permafrost thaw on the degradation, permafrost degradation on existing structures. And it's important to know that it's existing ones. We're not trying to develop something for buildings that will go up in the future. And that standard is basically going to apply to two different groups of foundations, either those that are shallow or those that are deep. And you see on this slide that in terms of shallow foundations, we have footings that either do or do not have a ventilated airspace. We have slab on grade with no airspace, typically used for construction in which we have heavy machinery or we have to have an on-grade construction. We can't elevate it in any way. Or deep foundations, such as those that are ad-freeze piles, which means they're put into the ground and the freezing back of the material around them, or simply they're bashed into frozen ground, provides much of the strength. Or rock socket or end-bearing piles, where the piles go deep enough into the ground that they're on solid material at the base, such as bedrock. So these are the foundations that basically exist in the north, and they're the ones that we're trying to develop a standard for. It's currently in draft form, and so further amendments are expected. So what I show you today may or may not end up in the final version, but I expect it to do so. The audience for the standard is something that we worked on for some time and with considerable discussion. So was it just for technical people? And the goal was definitely not to make it just for people who might be already very familiar with permafrost problems, but more like perhaps the audience in this room. So owners and operators of buildings, those that are actually owning them, the owners and operators of any other community infrastructure, building contractors, design professionals, educators, and regulators. So that represents, in fact, a pretty good cross-section, I think, of the individuals who are listening today. And I'm sorry that this is very small writing, but I'll attempt to walk you through it. The first question, if you have a problem with a building, is what's causing it? Is it in fact to do with seasonal frost heave or to do with progressive permafrost thaw? Could be something else too, but those are the two that we're looking at. And so at the top of this little diagram, we have problem identification. And what are the things that you're noticing about this problem, such as binding doors or windows, or cracks at the corners of windows and doors, perhaps cracks in load-bearing walls, and so on. So those are often the first sign that you've got an issue with potential permafrost thaw. And however, it could also be related to seasonal frost heave rather than to permafrost related. So we have to make sure that you correctly identify it, because as you'll see in a second, what you do for seasonal frost heave may be exactly the opposite of what you would do if it's a permafrost thaw problem. So it's very important that this problem characterization is correct. The standard doesn't really deal with seasonal frost heave, except at this point or the proposed standard doesn't deal with it, except to say that you detect frost heave generally in the winter, especially in the late winter. It's typically cyclical, so it'll come and go, and it might, however, be progressive. You can get jacking up, and so then you get progressive heave. The goal would be to limit seasonal frost penetration at that point. And actions might include ensuring good surface drainage, not removing snow, perhaps even banking snow, installing perimeter insulation just before grade, or considering regular releveling if you have that ability in the building. If you have permafrost thaw problems, then you're likely to detect them in summer, particularly in the late summer, because that's when the active layer reaches its maximum depth. They're likely to progressively increase, whereas seasonal frost may or may not. The mitigation objectives should be to slow down that ground warming and to reduce the rate of permafrost thaw. So we have warming first and then thaw that will take place afterwards. So again, luckily, drainage, which we've just heard about, community drainage plan, drainage in general around sites is good for either frost heave or for thaw settlement. And we need to ensure good ventilation if the building is up on stilts or on piles. We need to clear snow from around the buildings in winter. So again, the exact opposite of what we do for seasonal frost heave. And in terms of the snow loading that we've just heard about, great to clear the snow off your roof, but if it all ends up around the building blocking the ventilation, you'll have another problem on your hands. Consider installing insulation just below the grade or on the sunny side of the building. Consider shading on the ground, and consider possible releveling. Now, these are the things that an individual might be able to do, or a local operator of a building might be able to do. If at the end of all that the problem persists, then you need to consult a qualified professional. This is not just jobs for engineers. This is, in fact, what you need to do. It's not going to be resolvable by these simple solutions. If, on the other hand, the problem goes away, then don't stop doing what you're doing. You're now doing the right things. So this is just, if you like, a menu for construction, for operation. If this works, great. Otherwise, you need to do something else. And these are the measures that are going to be covered in the standard and their possible application. And so we have here the two groups of foundations, shallow foundations and deep foundations, surface footings, buried footings, or slab on grade for the shallow, adfreeze and grout-ended or bearing piles for the deep. Those three are the ones I've already discussed: shading, drainage, snow management. All of them apply to all of those different foundation types. But as we go down the various other things that you can do, such as ventilation, ground insulation, foundation adjustment and leveling, you'll start to see that they don't necessarily apply. You can't ventilate a slab on grade. That's pretty obvious. Mechanized refrigeration can be used everywhere. Thermosiphons, that we're also going to hear about and have already heard about this afternoon, can be used everywhere. Foundation replacement, rather difficult on slab on grade, although under rare circumstances it might be possible if the building is valuable enough. So, and what is the last one? Site abandonment, because in some cases you just can't solve this problem. The challenges of developing this standard are, first of all, how do we balance the individual nature of problems in an individual building? Can we define things sufficiently that they're general enough to apply across different buildings, different foundation types, yet sufficiently specific that we don't just say, well, invent a wheel, make sure it's round and turns. We need something a bit more specific than that. And so I think that is, in fact, the biggest challenge so far of the working group, was to even decide whether this should be a standard or whether it should be something that would be more like guidelines. So we're going to try and balance as well the appropriate technical language with enough information so that lay audiences can still understand what we're saying. And I think that's a second challenge. And ultimately, when you produce a draft standard, it goes out for consultation in the community. The first consultation was in fact the actual technical committee that will look at the standard, the draft standard that we're proposing, and either approve it or not. And their decision will also indicate whether we've reached the right balance, as I hope will all of your decisions. So when we put this out for review, we will look forward to getting your reaction back to see whether we've achieved the correct balance. So I want to thank all the working group members who have volunteered all their time, energy, and experience to do this. And I want to remind them that at the end of Thursday, when all the rest of you are going to the bar, we have a meeting. Thanks very much. Thank you.
And thank you, Tony. You just reminded me that I shouldn't stand between this audience and Miller time, so we'll finish this up. Our last speaker on working groups is Don Hayley. Don is a consulting engineer who focuses solely on Arctic regions. He was a senior principal of EBA Engineering Consultants for 45 years. Retired as Director of Arctic Resource Development in January 2013. He's an active volunteer in the capacity on committees for Transport Canada and Canadian Standards Association that address the challenges associated with northern roads and buildings. Don is the chair of the working group for buildings and permafrost support on thermal siphon foundations. So Don?
Thanks, Mike. Ladies and gentlemen, I have an advantage here over my previous three colleagues that I'm going to tell you what we have done, not to tell you what we are going to do, because our standard is in fact out for public review. So I'm a little bit ahead, but in fairness, we started early, I think. We've heard from Brent Walls something about thermosiphons. What's the right button here? Whoops. There we go. We've heard from Brent thermosiphons and how they work. Most of you, I'm sure, have seen thermosiphons. They're pretty much in use all across Canada now and have been for probably the last 20 to maybe even 30 years. And I won't go into details on how they work because basically Brent has told you that story. What I'm going to tell you is a bit of an overview of what we're doing with this standard and why we're doing it, who the group members are, and what the scope of the standard in fact is, and who we're focusing it on. And a little bit about the content. I'll have to skip over the content a little fast, but it is in the entire standard is in fact in a package on the front desk. So let's look into the past first of all to see where we're in fact going with this standard. The concept of using thermosiphon-like heat pipes to effectively accelerate cooling in civil engineering structures, the first major use goes back to the Alyeska pipeline, which was built in 75 to 79. And there they used a heat pipe called a cryo-anchor, same principle as the thermosiphon, but it's charged with ammonia instead of carbon dioxide. And it was used to cool the piles that support this structure because the piles are heavy and they were subject to creep. Now, just to go back to a question that was asked of Brent, McDonnell Douglas Astronautics were the first people to actually build this type of thermosiphon called a cryo-anchor, and they brought them to the market, civil engineering, and they sold them purposely as a methodology for stabilizing power poles in the ground. So that there's a history there of that, and they've been used to stabilize power poles, certainly in Alaska, for quite a long period of time. So when we go to Canada, we move 30 years into the future, and we look at how they're being used now in Canada on a routine basis, and that was really our task. To look at that and to come up with a standard that now makes sense where no standard currently exists. There's been a couple of high-profile projects in northern Canada that have relied on thermosiphons for their foundation design. This is the hospital in Inuvik, which has been in service now for a little over 10 years, and it in fact relies on a thermosiphon foundation design system, and it's quite a complicated foundation design. It's been well written up in the geotechnical engineering literature, and two papers were presented at the International Permafrost Conference in Fairbanks about 4 years ago. The other structure here is the Ross River School. Also an interesting case history, a large building built in basically a small community where most of the other buildings are in fact small wood frame structures that are supported on gravel pads or right on the surface of the ground. Suddenly now you have a large municipal building being built on a site with some very difficult permafrost conditions, and in my opinion, the only solution was a thermosiphon foundation system for that particular structure. The working group. You'll see some names here that are similar and appeared on the previous list. I'm pleased with the fact that we had a very good working group. All of the volunteers on the working group, when we worked together, are 62% northern residents, and virtually all of them have had real life experiences either in the design, the construction, or the maintenance of thermosiphon foundations. So we had a pretty good working group. So when we sat down to put together what the scope of our standard is going to be, the first question is, why are we doing this, and what's driving us the issue to actually have a new standard? And of course, the first one is that the permafrost is warming. The second is that thermosiphons offset the warming passively, so they don't require any power to operate. The system design installation is more complex than most building professionals realize, and this is very clear that when you start delving into what it takes to actually design, implement a program, and construct the building, it is very complex with a thermosiphon system as your primary support to preserve permafrost. And some installations have performed poorly and given thermosiphons a bit of a bad reputation. And the poor performance that's come has been linked to, really it comes down to the evolving technology. We're learning more as time goes on. A bit of a lack of understanding of how these systems should be designed from a systematic standpoint, and what's missing is often the operational diligence, and that's the whole monitoring side of them. You don't walk away from a thermosiphon system after it's in service and assume it's going to operate automatically till the end of life. So what we've written here is a scope that we agreed to, and is a scope that's in fact the standard. So our focus group, who's going to use this? We decided that it would be the planners and land developers, and those are the people who have the real interest in the building, in the site and the building over the long term. They're the people that have to live with the results of what we as design professionals give them. The design professionals who are working in the north, the architects, civil, and geotechnical engineers that are involved in the building design business, the contractors who actually put these systems together, the thermosiphon fabricators and installers, and we heard from Brent that there's really only one supplier in Canada now, and that's Arctic Foundations of Canada. And finally, it's the building owners, because without them buying into this standard, the ongoing monitoring simply will not be done. And that's been part of the problem that we've had with poor performance of some installations. But we have some scope exclusions as well, which I want to mention particularly, and that is that we are not dealing with retrofit of existing buildings. So these are new buildings that we're talking about, not to say it can't be done. It is not a common practice. There are no successful projects we can point to where this in fact has been used as a retrofit to an existing building. So we're staying away from retrofit. It's not something that we can really conceive. And we're not advocating thermosiphons for non-permafrost sites. So we're not, if the site is not clearly a permafrost site with a ground temperature that makes sense for your design, we don't advocate that it be used in our standard. Here's our table of contents. Here's what's in the document as it now stands. Two minutes left. And I'll let you have a look at that. We've got the scope, the definitions, performance, the geotechnical site characterization is laid out, construction, monitoring, all that good stuff. I wanted to point out that we, as a working group, we had to sit down and agonize a little bit about whether we should be really writing a guideline or a standard. And in the end, we compromised with our masters at CSA, who really had in mind that this had to be a standard. But to go from absolutely nothing to a standard, that's a big step. So what we did in the end is we adopted a text philosophy that says, say what must be done, but then follow it up with why we think it should be done. So that's the type of text that you'll see in our standard. For example, under subsurface investigations, it shall be undertaken, a subsurface investigation, but under the notes, it says why it needs to be done. So that's the approach that we've taken. In terms of the sections here, we've got a background section, we got references and all that good stuff. We have performance requirements in the next section, and service life. And I'll talk about service life in a minute. We have the geotechnical site characterization, what you really need to do, and take a phased approach to it. The system design that we start with fundamentally, you need to ask yourself, is this the right system for this particular building? So we give some guidance on that. The thermal analysis and modeling gets a lot of coverage. We put a lot of effort into that because we think that in some projects that has been missing or not done adequately. And we talk about the analytical tools available to the designer. Now, climate parameters are very important, and we really stress climate parameters. We stress that we have to know the lifespan of the proposed building. In the case of the Inuvik Hospital, it was clear, we were told 30 years. New buildings now are somewhere between 30 and 50 years, but that decision has to be made by the owner of the building. And then we have to look at the input that we put into our thermal analysis to represent the climatic conditions over the life of the building, not only the trends, but also the extremes, because we have to handle both in our design. And for that, we basically adopt and follow the procedures laid out in this CSA guide, which is 2 years old now, and that many of us in this room worked at preparing, and we feel that it's an excellent place as a first start. Complex buildings, you may have to do more, but certainly for an average building, it's a great start. The system design considerations are all covered, how the system fits in with the rest of the building. It's in there in a section. The construction is dealt with under the site preparation, the timing, when to put them into place, and how to install them. The monitoring plan. Now, monitoring plan and its implementation is very important. Some people will say, well, why aren't you dealing with maintenance? Well, with a thermosiphon system, there really is no maintenance. It's just a matter of monitoring. They either work or they don't. So you have to monitor to ensure that they keep working. So we end up with some annexes and with some information tied to the end, and then now we look for your feedback. So it's out there for your review, your comments. Take it with you to those that you know that are actively using thermosiphon systems, and we'd sure like to hear your feedback before we go to the next step. Thank you.
Yeah, thank you, Don. I'm really pleased to see that our first of our standards is out for public review, and I would encourage everyone who has an opportunity to go take a look at that. We would really appreciate your feedback on it, because hopefully it'll be something that's very useful for the design community and building owners as well in future. At least, like we said, for the moderate buildings, the more complex ones certainly might be a challenge right now. In another comment I'd just like to make on that, there was a reference there to site development. With permafrost sites or sites that are susceptible to permafrost, you may only get one chance to get that site properly prepped to get a thermosiphon foundation in without having to take some extraordinary measures. So I don't think enough can be said about how you approach the site to begin with, whether you strip it or what you do, and you prepare it before you put your thermosiphon foundation in. Because if you're a developer or if you're a contractor or whatever, and there's an expectation that the building's going to be completed on a certain schedule, and all of a sudden you lose that site for a period of a year while you have to restabilize the permafrost, there's going to be some real concerns with that. So I can't emphasize how important that whole site approach to the site is in the beginning. So with that, I'll open up the floor to questions on any of the topics that you've heard today. So if there's any questions, feel free.
David Malcolm. I have a question for Heather. With regard to a discussion of snow load, I noticed that very little consideration is being given to monitoring snow density. And, given that climate warming tends towards wetter snow, denser snow, and an increase in extreme events, should it not be given more consideration to monitor snow density?
Yes, definitely. Snow density is probably 60% of the problem in a lot of communities. We do mention how to monitor the weight of the snow, how to take a core and weigh it, but some data is better than none. So for those communities that really do need those measurements in the communities, but for those who don't want to go with the full weight of the snow, which is absolutely what's needed, a snow depth is acceptable. Stick a ruler in the ground, and here's how you do it and where you put it. So the snow depth data is still helpful, but absolutely the whole story is really told by what's called a snow water equivalent, the weight of the snow measurements. The densities are important. We had hoped that they would have been calculated or looked at for the 2015 building code. That job didn't get done. There were some cutbacks in the government. So it's on the plate for 2020. If nature doesn't and collapses, don't say do it sooner. But no, density is really important.
Sorry, do you have any other questions for the panel, any of the working groups? Well, maybe I'll just, we have a few minutes here, I'll just ask the working groups themselves if there's any one particular question that in their mind that they would like to receive feedback on from the various stakeholders around the north. So maybe Ken, is there any particular question in your particular standard development that you'd like to see? Not this time. You don't need any more questions? Okay, Don, anything in your area?
Well, we're out for review, so hopefully people will. I guess our hope is that people will actually look at it and give us some genuine feedback. So that's.
Okay, thank you. Tony?
Well, as I said, I think our biggest challenge is the question of will we achieve the correct balance? Is it indeed even possible to create a standard when so many situations are unique? We're still working towards the optimistic side, and as they were referred to, our CSA masters have little whips to make sure that we indeed get there. But I think it is in fact a challenge that we don't go so general that it will apply to everything, but then be so general that it's not very useful. So I'm hoping we will achieve the right balance, and I'm hoping that when we finish this phase, that we will get feedback to make sure that we have done so.
Okay. Heather?
Data. I need data. Anybody got data? I'll take it. I'll do lots of neat things with it. Snow data is an issue. There's a shortage of it. I guess I'd like to know if communities would be interested in monitoring snow. You don't have to do it every winter, just those snow winters when your buildings may be at risk. It's not, and we're not talking every day. We're really talking maybe once a week for 3 or 4 measurements a year. But it really could make a difference to your buildings and your safety of the citizens in your community in those vulnerable buildings. So we really have to know how much snow is there to know how risky the situation is. So that I think is one of the big challenges. The other one, just to reiterate what Tony said, is is how to strike the right balance is going to be a challenge. We talked about having a pull-out section. I mean, when you talk about building codes, it gets pretty techy. So how do you boil it down and make it so that somebody can use it? Somebody in the community knows when they're at risk and knows what they have to do to reduce that risk and how to clear the snow without killing themselves or tearing apart the building at the same time. So that's going to be a challenge.
Thank you, Heather. And that one in particular about how to address the snow load once it's there is an issue. We know we also have another situation that recently occurred last winter where we had a significant snow load on a roof of a building, but there was a rapid change in temperature on a metal roof, and several feet of snow slid from a higher level roof onto a lower level roof and ended up cracking the roof trusses on the lower level due to the impact. So there's other implications about snow clearing that we have to do.
Hi there, microphones. I just had a comment rather to add to Heather's data needs with respect to this. And last year I heard of a site that looked at snow depths that was actually came across CryoList that Richard Kelly at University of Waterloo was asking for, and it was snow tweets, and it was getting snow depths by using social media, by using Twitter. And I was wondering if you could maybe just comment on using that and also maybe like a qualitative assessment of snow density, like breaking it into 3 different divisions, if that would be helpful, and what the viability of something using social media in these communities would be.
Okay. The measurement of the snow depth is fairly easy. It's just a good old-fashioned ruler in the ground, as long as you don't pick a snowbank to do it in, and you take a few measurements and you average them. And that's quite doable, and the tweets would be great to monitor what the current conditions are. It's still a bit of a challenge to know what, how extreme is that, or how close is that to what the community might have used for designs. But it would be a great way to get data. It certainly would be helpful to know when there is an issue. It might be, in fact, as I say, increasing snow loads are here to stay for a little while. So it may be an issue that we have to eventually get emergency management coordinators involved in, because in a community it will be a heavy snow year, but not all buildings will have the same risk. But for them as well to have those kinds of measurements would also be very helpful. So yes, it would be very helpful to monitor what the ongoing severity of the snow condition is. And if they happen to have a little snow tube, or someone could make sure they have a snow tube in a community, that would be even better, but I'll take a ruler too.
Yeah, I wondered if you could tell me what the legal status of a standard is.
So you're looking for the legal status?
Yeah, you talked about, you mentioned the CSA plus 4011, which is a guideline. So if you don't adhere to that, you just didn't adhere to the guideline. But once you create a standard, what is the legal status of that? If a person builds a building which doesn't adhere to the CSA standard, and there's a problem, does that presumably is something that is considered in recourse in disputes?
It's a good question, and the answer lies in how and whether the standards are adopted by the jurisdictions of Canada. So if the northern jurisdictions adopt the standards in some form of legislation, then yes, they're enforceable through that legislation under say they're adopted along with the National Building Code for your particular area. Then that would become an enforceable standard in that jurisdiction, and yes, presumably through if there was a problem, then the process would address the fact that someone didn't follow a particular standard. However, I would like to mention that even with the existing National Building Code, standards are minimum requirements, and usually they're developed as such. So it doesn't replace good engineering practice or good architecture. So the intent here is that the standards set a baseline that people don't fall below. But if good engineering practice suggests you should do more than what's in the standard, then you absolutely should. And snow loads is a great example, and I've talked extensively with a number of designers in the north, structural designers, about snow loads. And typically, they do not use the National Building Code information on its own to design roof structures in the Northwest Territories, because they need to be more conservative of that, especially with the changes that are happening. So I think if you look at the standards as a minimum requirement, but you still have to do the due diligence and the good engineering practice, or follow good engineering practice with regard to how to design for a particular environment. Do we have any other questions for the committee? Okay. If not, I'd like to thank the chairs of the working groups for all the hard work on this. There's some very challenging areas, and some of the areas actually overlap. So I'm sure it's been a real trial by fire for the last few months or years. So I appreciate looking forward to the completion of the 4 standards. And I'd also like to thank members of the audience who participated on the working groups or on the technical committees. They're instrumental as stakeholders to ensure that we get a broad base of feedback on the development of the standards, that we hopefully cover all the bases when we get things out for public review. And also for those of you who take the time to review the standards that we do produce, I'll thank you in advance for that, because that's going to be key to us finalizing the actual documents and putting them forward for use, for public use. I'd also specifically like to thank Sarah Brown and John Straker, the 2 co-chairs of our technical committee. So with that, if there's no other questions, I'd like to thank you for listening. Oh, I have one in the back there.
Yeah, 2 questions online from Ian Church. One of them regarding snow loading. He asks, are you considering dynamic loads moving avalanching off roofs? And the second question from the same person is drainage. Are you considering the Arctic northern situation?
So let's try the snow loading first with regard to dynamic snow loading.
It mentions it. The standard, we had to try and keep it simple because there's a lot of different types of buildings out there. So it still being refined, but mostly refers to what a measurement of snow would be in the community, and then it gives some examples of where the vulnerable buildings, what kinds of attributes of buildings might make them more vulnerable. So if you've got a heavy snow year, what kinds of buildings need to have a close second look about snow load? So in that sense, it does cover it. It doesn't go into the details that are in the building code if you're designing a brand new building. It's looking at the risks for an existing building.
Thank you. And for drainage?
The short answer is yes, but I guess that is reflected in the committee members we have is certainly diverse, covering all the territories, and I think multidisciplinary. So I think that's how we're covering off in terms of the consideration of the Arctic North in drainage.
Okay, if there's no other questions, I thank you very much for your time, and again, I thank the working groups and wish you a good evening. Thank you.